By the end of this video, I'll expect you to recognize and count the various components of a logical data structure. Rest assured, I do not expect you to understand what all of these symbols mean or how we use them, but this is dense material, so hold on to your butts. Alright, so here's an example of a data structure for a photo gallery application. Again, there is a lot here. We will break this down piece by piece. The purpose of this notation is to represent what real users have told us about their needs. And by writing it this way, we can better understand what kinds of data the system needs to store. If you count with me, we have 1, 2, 3, 4, 5 of what we call entities. That is 5 kinds of things that we want to remember in and of themselves. We have camera, photo, gallery, collection, inclusion, and collection. Each entity represents something that we may store many of. For example, we may have thousands of photos in our library. We may have used many different cameras over the years. This diagram shows not only that we store photos, but all the details we remember about each photo. We call those details attributes. For example, about each photo, we can remember a file name, shutter speed, many other things. File path and shutter speed are attributes. Attributes are written inside the boxes. There are a total of 19 attributes on this diagram. Next, we have relationships. If you count with me, there are 1, 2, 3, 4, 5 relationships on this diagram. A relationship is marked as a line connecting two entities. For example, this line says the photo and a camera are directly related ideas. That is one of 3 relationships on this diagram called one-many. Notice that these 3 relationships have a symbol called a chicken foot on one side and not on the other side. The chicken foot means many, and the lack of a chicken foot on the other side means one. If you imagine making a diagram where you draw lines connecting cameras to photos, for example, the chicken foot represents that idea. The other 2 relationships on this diagram are called 1, 1. They have no chicken foot on either side. That means for each instance of one entity, we can remember one instance of the other entity and vice versa. For example, this says that each photo can represent one gallery and each gallery can be represented by one photo. You can think of each relationship as a two-way street. About each photo, we can remember at most one camera. And about each camera, we can remember multiple photos. Well, these are 2 separate ideas. And by thinking about each relationship as 2 separate links, we can reveal a lot more about the requirements of our system. Take the number of relationships, multiply by 2. In this case, 5 times 2 is 10. Links can have labels. These help us understand the nature of a relationship. For example, each photo can represent a gallery. Each gallery can be represented by a photo. Links can also have a degree, which can be either one or many. It will have a chicken foot if it's many. So this link here says that about each camera, we can remember many photos. This is called a degree many link. About each photo, we can remember its camera. No chicken foot. This is called a degree 1 link. Notice that in both cases, the symbol is on the opposite side of the relationship from the entity that we're describing. That's only the case for chicken foot. For labels, which we were just showing, and bars, which I'll get to later, they're shown right next to the entity that we're describing. There's a special kind of relationship called a to-be relationship. It's labeled B on both links. This relates entities that are different ideas, but might be the same physical thing. I have collections of photos. Some of those collections might serve as galleries if I choose to share them online. So that collection is really the same physical thing in a different manifestation. Contrast that with the photo gallery 1-1 relationship. That's relating to very different entities. This distinction is not obvious, but it will affect how we use the model later. So we require that all 1-1 relationships be labeled. So relationships are either to be or not to be. Thanks, Hamlet. Every other kind of relationship, including one-many relationships, are also not to be. So we have 1 to be relationship and 4 not to be relationships. The last part here is the trickiest part of an LDS. Count with me the identifying descriptors. 1, 2, 3, 4, 5, 6, 7. Identifying descriptors are used to tell one instance from another. If I return again to this example, about each photo, we can remember, among other things, a unique file path and a shutter speed. Notice here that 2 photos could have the same shutter speed, but no 2 photos could have the same file path. We've chosen file path as an identifying descriptor. You can have more than one identifying descriptor, and when that is the case, what we're looking for is a unique combination. There's an official way you read this. About each camera, we must remember its manufacturer and its model name. No 2 cameras may have the same manufacturer and the same model name, but 2 cameras may have the same manufacturer or the same model name. That set of identifying descriptors is called an identifier. That's different than an identifying descriptor. An identifier is a set of identifying descriptors. This pair of 2 identifying descriptors is one identifier. This file path is an identifier which contains just one identifying descriptor, set of size 1. We said here that there's 7 identifying descriptors on this diagram, but there are only 5 identifiers. 1, 2, 3, 4, 5. That is 5 sets. Inclusion and collection here, you'll notice, has another identifier which includes 2 identifying descriptors. And those are placed on the links. What? These have exactly the same meaning, but it's a little less obvious how you read them. When a bar is placed on a link, what we're saying is that the associated entities are the things that need to be unique. So this inclusion and collection must have a unique photo and collection pair. So there's 5 identifiers, which is no surprise because we have 5 entities. That is usually the case. But I said that each entity must have at least one identifier. To notate more than one identifier on the same entity, we must use 2 different symbols so that we can tell that these are 2 different identifiers as opposed to 2 different identifying descriptors in the same set. These are 2 separate sets. So here I used a bar and a zigzag. This is a rare situation, but when would this happen? Suppose we ask a user, how do we tell one photo from another? One user says, well, each photo has a unique file path. No 2 photos can have the same file path. Great, we write a bar under the file path. But maybe another user says, hold on, I can have one photo that has 2 different file paths if I rename it. But I know that those 2 files will contain the same date taken, and so I know that those 2 files represent the same photo. And so that's how I tell one photo from another. So now we have 2 users who have declared 2 different identifiers. I'm not going to say which one is right. The point here is that this is a notation that can be used to capture user input so that we can have a conversation and find the answers to these questions. Now check your understanding. Please count how many of each of the following are included in this data structure.